Hey guys, this is Professor Bood coming to you from Beijing. I just wanted to make sure that everyone understood what we did last week. Make sure to review, some of the material that we did last week. It was the melting point was very basic. I think the thing to take away from that is this paragraph. If you really understand the second paragraph, which talks about when you mix two compounds that are not the same. Two solid compounds that are not the same, the melting point is going to go down due to impurities. And the thing to take away from the TLC, well, I think the TLC, you should really understand that procedure. Essentially, how the movement of your substance depends on whether it's polar and whether your solvent is polar. That's basically it, though. Just make sure to review that briefly. Okay, so this week I'm super excited because we are doing a fractional distillation. Now, you guys, I don't know how much you guys know about distillations, but I will try to do my best to explain it because it's in one sense it's pretty basic, but in another sense it's actually very complex. So we're gonna in lab this week we're gonna do distillation and gas chromatography. So distillation is to put simply, is just the separation of two or more substances by boiling point. So if you guys remember your metha, etha, buta prefixes, so you've got, for methanol, you've got only one carbon, and then you've got the alcohol group. For ethanol, you would have two. Propanol, you would have three. Butanol, then you have 4 carbons, and you've got the alcohol group. And then octanol, obviously you would have 1, 2, 3, 4, 5, 6, 7, 8 carbons, and your alcohol group. So the reason why this one is more soluble in water is just because about 1/4 of the molecules attached to the carbon are essentially nonpolar. But 1/4 of them are polar, whereas with the octanol you have many more nonpolar, and only one small section is polar. So this doesn't really have to do with. This is an important concept to remember, and to remember the name. So this week we're going to be working with an etha and with a buta. So we'll cover those a little bit more in detail. So essentially you have to remember that there are a few things that change the boiling point. The polarity, so how much the substances want to be with each other, as we covered last week. So here's a nice picture of boiling, and here's a nice picture of water being polar with itself. So this is why water is so hard to evaporate. If it was nonpolar, water would evaporate very easily. Another important force to remember that stops that increases the boiling point is the stronger the intermolecular forces, similar to like in water, the less it's going to want to boil. So I tried to find a picture of intermolecular forces, but it's kind of a poor picture, but it kind of demonstrates the point. So the more that these molecules want to be with each other, the higher the boiling point is going to be, because they're not going to want to evaporate. So obviously, if they don't have a very weak attraction, they're going to have a lower boiling point. And the molecular weight also matters a lot in boiling point, because it just becomes more difficult to heat that molecule, to make that molecule excited into a gas phase. So, for example, in hydrocarbons, you've got all of your short chain hydrocarbon is just like any carbon and hydrogen is basically what it is. So methane, I hope you guys have heard of methane. Methane is just CH4, and it is always in the gas form at room temperature, whereas gasoline, gasoline's not a pure substance, but gasoline is basically a really long chain hydrocarbon. It's got about 12 to 14 carbons, is going to be a lot more difficult to evaporate, and the very long chains like motor oils, and obviously those are still not pure, but those are going to be even more difficult to evaporate. So gasoline will evaporate at room temperature, but it is a liquid at room temperature, whereas your motor oils will not evaporate even at very hot temperatures, which can be found in your car engines. Okay, so the larger the molecular weight, the less likely it is to boil easily, so it'll take longer to boil. And finally, there's the size and shape. So if you've got a bent molecule, it'll be harder to boil, or it'll be easier to boil, sorry. And if you've got a straight chain molecule, it'll be more difficult to boil. And some of that has to do with the surface area, but I won't go too much in depth into that. So this week we're going to be playing with substances very similar to ethanol and butanol. We're going to be playing with ethyl acetate, which is right here. So it's essentially just an acetate group, an acetate functional group, which is just this double bonded O, this single bonded O, and this extra carbon over here, and a carbon in the middle, with an ethyl. So if you remember, ethanol has 2 carbons. So ethyl acetate will have 2 carbons right here. So if we compare that to ethanol, ethanol's got the alcohol group and the 2 carbons. And we're also going to be playing with butyl acetate. So you've got the acetate group, and you've got 1, 2, 3, 4 carbons. Very similar to butanol, which has 1, 2, 3, 4 carbons, and the alcohol group at the end. So those are the ones that we're going to be playing with. So remember, longer chain is a higher boiling point. And we're going to be doing a boiling point mixture. So we're going to have 2 substances that we mix, which is going to change the boiling point of each one of them, and I'll talk about that a little more. So why am I so excited about distillation? Well, distillation has a long history. In the good old days, in the days of Prohibition, you had whiskey stills that were illegal. And so here's a nice demonstration of a pretty crude whiskey still. They would just throw in their fermented beer or whatever they wanted to distill, and all of that alcohol would evaporate up, and then up here it would cool off and condense down into this big pot right here. So that's essentially the very, very basic crude distillation. Here's a more modern, very, very crude distillation. Some guy in his underwear distilling off whatever he fermented into this gross-looking can, and then calling that moonshine. So more beautiful distillations tend to be found in the oil industry. So in the oil industry, you've got crude oil, which is made up of carbon chains like methane that we just talked about, like gasoline, and essentially they distill it, but they have all these different points at which they pull off different things. So obviously the thing that will evaporate first is the gas. So that's going to be like your natural gas, your CO2s, your methanes will evaporate off here. Then you've got naphtha, and as we get longer chains, you've got gasoline, you've got kerosene, and all the way down here you've got oils, and then you've got coke, which is actually just essentially carbon. So the boiling points will be higher, up here, which means that they're more difficult to evaporate, which is why they have to heat them up so much. And the boiling points will be lower up here because the column will be very cool here, and they can still recover that. Okay, so that's fractional distillation in a bottle. That's distillation in a bottle. Fractional distillation is interesting because you've got 2 things happening. You've got the hot vapor, so your heating element is going to be on this bottom of the flask, and it's going to boil off a little bit of your material, and that material is going to be in gas form. It's going to start going up, but then at some point it might cool off, and it'll start coming back down. And see, that's what the L3s and L4s are for. So essentially, as the liquid cools off, it'll start falling back down, but then it'll get heated up by more vapor coming up. And so what that's going to do is it's going to separate your mixture a lot better. And to demonstrate that, I've got this graph which you've got in your lab manual. And this may look pretty confusing, but it's actually not too bad. So essentially, this is your mole fraction of whatever substance you're using. So if it's 100%, let's say ethyl acetate, or, well, yeah, I think that's what we were using, then you would just be right here, and you wouldn't have to worry about distilling. But let's say we're using like a 50-50 mixture. So we would essentially start right here and go up, or let's just to stay with their example, let's say we're using a 78% mixture. So we would start right here, and we would bring it up to heat, and this will tell us how much of our substance will be in the liquid form, and then if we move over to here, it'll tell us how much will be in the vapor form in the next step. And then, you know, as you distill it, it's going to kind of go like this. And so you're going to get more pure and more pure as you get near to the top of the distillation column. And that'll vary with temperature. So here we've got our nice little graph. So here's your mole percent ethyl acetate and butyl acetate. So I guess we're going to probably start with something like 75% butyl acetate, or we're going to want to... Yeah, anyway, I'll explain this a little more in the lecture or in the lab. But that's essentially the basics of it. So then, you know, once we get your sample, so we're going to distill it, and it's going to increase in purity for one of them, and then the other one will boil off later. So which one will boil off first? Looking at these, just by looking at the length of these, so we've got ethyl acetate and butyl acetate. I think ethyl acetate's going to evaporate off first because it tends to be a shorter chain, and I think in the lab it tells you what they evaporate at. Somewhere around here. Anyhow, that's not terribly important. So this is kind of the setup that you're going to have. You're going to have your little your butyl acetate and ethyl acetate in here. You're going to attach that to a fractioning column, which will have the vapors going up and the liquids coming down. And then once you get all the way up to here, your vapors will cool off and they'll come down through here. This is going to be cooled with water, so we're going to have water flowing through this to cool it off, and then that'll just help your gases liquefy again, and then when they liquefy, they'll just drop into your tube right over here. So then once you've got your sample in your flask, right here, or in your volumetric flask, you can then take that sample over to the gas chromatograph. And so what is a gas chromatograph, you might be wondering? Well, I have an answer for you. The gas chromatograph is very basic and simple, but it's extremely useful because it allows you to take a liquid substance, and when you inject it into your gas chromatograph, that liquid substance will then be heated into a gas form, hence the gas chromatograph, and it'll travel along this column of packing. And what this column of packing will do is essentially help separate out the small and big molecules a little bit. So the small molecules will fly through a little bit easier. The big molecules will they'll struggle trying to get through. So your ethyl acetate should come out first. Your butyl acetate should come out second. So this will think that this is your ethyl acetate and butyl acetate. You will then analyze your what comes out, and something like this is going to be what you get. So it'll show essentially what the substance that you're getting over time. So we're gonna start a chromatograph. Nothing's going to happen. Then we're going to get boom, one peak. That's probably going to be ethyl acetate. Then we might get some other. If we have impurities in our ethyl acetate, which we shouldn't, we might get little bits like this. And then a little bit later, boom, there's our second peak. That's going to be your butyl acetate. And how high that peak is indicates how much of that substance there was. So that's how we're going to analyze the samples. So that is basically what we're going to do in class. Here he's got a nice little picture of injecting your syringe, because you're going to use a syringe to inject into the gas chromatograph. And we're going to hook those up to the lab quests like we did last week for the temperature. And that's basically what we're going to do this week in lab. So hopefully this helps. If you have any questions, feel free to shoot me an email. Please read through the lab before you get to the lab. And I think this week should be a lot of fun. So, alright, I will see you guys in class. Talk to you soon.